remember, your job is to be memorizing these basic curves, the shape, the equation, and the name. Okay, so the next one is the logarithmic function. And because we use natural logarithms more than we use common logarithms in upper math, they call it the natural logarithmic function, but it's really the logarithmic function. So the equation could be ln x, it could also be log x, depending on which kind of logarithm you're doing. The shape of the curve contains the point 1, 0, that's important, and is asymptotic, well, it's asymptotic to the negative x-axis, or negative y-axis. It looks like this. Now, I want you to be careful, because that actually looks kind of similar to one of our other ones. Which one does that look sort of similar to? Well, it has some definite likenesses with the exponential, but the shape of it is very much like the square root function. The difference is the square root function starts at the origin and shoots out like that. Haven't we had that one already? Yeah. The logarithmic function follows the negative y-axis down. Did I turn this on?
Yep.
Yeah. Okay. All right, so that's ln x. The sine function. Now, for this one, sine, S-I-N-E, is the name of the function. The name is on the paper. The equation is sin x. And I know we're in a religion room, but we don't say sin x, we say sine x, right? This is sine. And when we sketch it, I need you to be careful, and I know those boxes are small, so you can make the scale anything you want. But label 1 and negative 1 somewhere on your y-axis. Don't just go up one box. Go up several boxes and call that 1. So you have a little room. Because the whole curve is going to operate between 1 and negative 1. In a later chapter, I think chapter 4, we will be spending time accurately graphing all kinds of sine curves. All you need at this point is to know, put a dot at the origin, make a hill that goes up to 1, and then however wide you made that hill, make a valley the same width that goes down to negative 1. So if you used 4 boxes to make your hill, use 4 boxes to make your valley. And then go in the opposite direction, same thing. Put arrows on the ends because that curve goes on forever and ever and ever. Up and down, up and down, up and down, forever and ever. That's your sine curve. Now your cosine, COS, cosine curve, is exactly the same, except instead of going through the origin, still got the 1 and the negative 1, still got the hills and valleys, but it looks like this. So do you see the difference? If you start on the axis, you actually start up here at 1. When you do a sine curve, you start at the origin. It's as goofy as can be, but how I remember it, as a good little Catholic girl, original sin. Sine goes through the origin. Original sin. Sine goes through the origin. Cosine does not. Otherwise, they are exactly the same picture. So they're going to have all the same features in terms of boundedness and continuity and all that, because they're the same curve. They're just shifts of each other. That's the cosine. All right, the absolute value, that's an easy one. You all know what shape is an absolute value?
V.
A V. So your absolute value function, and there's the equation, but we know if we put it into our calculator, it's ABS, right? That's a B. Remember, if we put it in our calculator, we got it, that's the button. So there's your equation, and here's your picture. It's a nice little V straight out from the origin. The greatest integer function is my least favorite. And there are different notations. I like to use the bracket notation. Your calculator is INT, and that's located in the same place that the absolute value is located. You might see other bracket or other notations. Sometimes there's like a double line here. Pick one. Pick a notation and stick with it. And it looks like this. Now be careful when you graph this one, because this is another one like sine and cosine, where how you get started makes a difference. Put a dot at the origin, and go straight over. I don't care how many boxes you go over, they're so tiny. Maybe go over 2 or 3 boxes and put an open dot, and then jump up. This is 1, and this is 1. Then jump up and put a closed dot, and take another step, same length. And then up another one, over, same length. So all of these steps are 1 unit wide and 1 unit apart. I always think I'm going to put different graphs on here, and I always forget to do it, so you have more room. But these are 1 step wide and 1 step apart. 1. That's your greatest integer function. And finally, the logistic function, which is probably the most applicable to a lot of things you do in science class. The equation, there's the equation of the basic logistic function. E, because that's the same letter. What other function has the E in it? The exponential. And that E is Euler's constant. It's also the base of the natural logarithms. Right up there with pi in importance in math land. It's another irrational number, goes on forever and ever. That's what that is. It's a button on your calculator. We have to press in the end, we'll find it. It's a button on your calculator. Okay, and it looks like this. This is 1. So I'm up 1 unit. So I've given myself plenty of room there, but that's 1 unit. I'm up 1 unit. Have an asymptote there. Have an asymptote here on the axis. And a curve looks like this. It's that squiggly line like we have with the cubing function, but it's sideways. It's sideways. And those are your BFF. So you need to start right now memorizing the equation, the name, and the picture. Okay? Now, just for fun, let's do a couple of function analysis. So you pick the curves, and we'll fill in all the other stuff that goes with it just for practice. You are not memorizing all this other stuff. We're going to figure it out as we go whenever we need it. Okay? But pick one. What function do you want to do it with? Any of the 12. Absolute value function. Okay. So I am going to answer all of the questions. All of the questions based on this picture right here. Okay? So the first question is a domain. What's the domain? All real numbers. So negative infinity to infinity. There are no breaks in that. X goes forever to the right and forever to the left. No breaks. What about range, though?
Y is greater than or equal to 0.
So 0 to infinity. Y is greater than or equal to 0. Every part of that picture is at 0 or higher. Continuity. Would you say this thing is continuous? Yes, on its entire domain. It is continuous from negative infinity to positive infinity. You never pick up your pencil one time. Increasing or decreasing? Both. So we need to specify that. So the first half of it is decreasing. So from negative infinity to 0, from negative infinity to 0, we're decreasing, right? But then, from 0 to positive infinity, we are increasing. Now, if you think of, like this function right here, the logistic function, does it do both? Does it increase and decrease? No. This one is strictly increasing. As you draw it from left to right, your pencil is moving one direction, up.
For those, it doesn't matter if you don't use brackets, right? It's just always parentheses.
Right, for increasing, decreasing, yes. The only exception to that would be something like the square root function. No, still, even then that would be a parentheses because it's not increasing at this point. Yeah, so it's going to be parentheses all the time. All right, what's next on the list? Symmetry. Now, lots of things have symmetry. We are only interested in the special symmetries, okay? So does this curve have any of our special symmetries? And remember, that's x-axis, y-axis, origin, and identity. Does this one have any of those? Which one? Y-axis. So for symmetry, this one has y-axis symmetry. You can tell from the picture, but you can certainly tell if you put a negative in here, if you change the sign on x, does it matter? No, not when you're taking absolute value. Reed, is your hand up?
Yeah, I'm just kind of confused on how to find symmetry.
You have the tests of symmetry. You change the sign on x, that's y-axis. Change the sign on y, that's x-axis. Change them both, that's origin. And switch x and y, that's the identity line. So we have a whole sheet of paper, both sides, all about that. So look that back over, but you got to learn those rules. This one, really, I mean, obviously, it has symmetry about the y-axis. I mean, look at the picture. It's the same on both sides of the y-axis. So that one you can tell without really doing a test, but you can always do the test to get that. All right, boundedness. Does this curve have any boundedness? And remember, it can be above, below, Or if it's both, we say it's bounded. You just bounded, period. So, below, there's a floor at y equals 1. Or y equals 0. Y equals 0. There's a floor at y equals 0. So it's bounded below. Extrema. Extrema are maximums and minimums. Does this curve have either one? A max or a min? It definitely has a minimum. And it would be both a local and an absolute. Minimum at the origin. None of the basic curves are going to have local and absolute that are different because they're just the basic curves. It's when we start making adjustments and getting weird things that look like this, that would have two local minimums, but that one would be the absolute. None of our basic curves have that kind of situation. Horizontal asymptote. Does that picture have either a horizontal or a vertical asymptote? None. None. And then end behavior. This is the kind of the new one, the tricky one. End behavior. End behavior means what happens to the curve, to the picture, as x heads to infinity and as x heads to negative infinity. So in other words, as the picture goes to the left, that's negative infinity, which direction is your pencil going, up or down? Up. So you'll say positive infinity. As we go to the left, this part says left. This part says up. As we go to the right, my pencil is also going up. So your end behavior is up, up. Some of the curves, look at the pictures of them. Some of them are up, up. Some of them are up, down. Jacob?
So when we want to see like where our pencil is going, would you like start at the origin to do that?
Just ask yourself, as you go to the right, are you going up or down with the curve? As you're going to the left, are you going up or down with the curve? It's end behavior. It's as you approach the ends of the paper. Are you heading up? Are you heading down? What are you doing?
Well, you're heading up on both sides.
Up on both sides. That's right. It says positive infinity. Doesn't matter whether I'm going left or right. I'm ending up on both sides. Right? All right, let's do one more. So pick another function. Let's not do one of the weird ones. Let's not do sine or cosine. Let's do one of the basic functions that don't have some randomness associated with them.
Cubing function?
Square root function. All the same question with the square root function. Okay, so the square root function is y equals root x, and it looks like this. Okay, so what's its domain? Be careful. What's its domain? 0 to infinity. And kids, that makes sense to you. Because whatever is under a radical has to be greater than or equal to 0, right? There it is. Right there's the picture of it. What about its range? Same thing. The range is the same thing. Because isn't the lowest point 0? and then it's going up, up, up. Now it's going up more slowly, but it's still, if you go far enough, it just keeps going up, 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 up. Would you say it's continuous? Yep, on its domain, it is continuous. Would you say it is increasing or decreasing? Increasing from 0 to infinity, it's increasing, and it is never decreasing. Look at the picture. Does it have symmetry sideways? No. Does it have symmetry this way? No. Does it have symmetry this way? No. Can you switch the variables? You can, but you get a different equation. This one has none of our symmetries. Would you say it's bounded anywhere? Below, at y equals 0. Doesn't go below 0. There's a floor at 0. Doesn't go below. Does it have a maximum or minimum point? It has a minimum at the origin. And what about its end behavior? Now, this one's a little tricky because this says what happens as we head off the page to the left. Does this picture go off the page to the left? So that's doesn't have one. There's nothing on the left side. You can't analyze the left side of the picture because it doesn't exist. But what about the right side? As I go to the right, what is my pencil doing? Going up. Well, you would say none or something, because there is no end behavior on that side because there's no picture over there. Okay, well, if you want to on your own time take a look at a couple more of those, feel free. But again, we just did 2 examples and we based everything on the picture. So if we know the picture, then it's easy to figure out what's what. Okay, the next page, we're going to talk a little bit about some transformations. And I think you guys, you seem to be really good with these, so I think this will be simple for you. But again, you got to know the shapes. So we're going to graph y equals the absolute value of x plus 1. Now you know what shape you're graphing, right?
No.
You have to go golf.
Yeah.
Is that because we're sectional?
Yeah, we gotta
number
keep
2?
going
Gotta
now.
keep going, okay. So this is a V. What about it? What's this look like? Instead of V'ing from the origin, it's going to V from -1. Do you remember that when you put a number kind of inside the problem with the x, so those aren't parentheses, but they're kind of like parentheses, when you put it in there with the x, it shifts you left and right. And it's always the opposite of what you think. So +1, you might think is right, but it's actually the opposite. It's left. All right, that's easy enough. What about this one? What's this one going to look like? It's a parabola. We know it's a parabola because it's a squaring. It's a squaring function. And I've kind of done the same thing. I've stuck a number inside the parentheses, which is going to move it 2 units to the right. So you're just going to have, oops, I should always label that point. You're going to have your nice little parabola over here. That's all. Just a quick sketch. Nothing, fancy. You don't have to plot a bunch of points. Just get it in the right spot. All right, now, what about the next one? That is different. This is different than this. Does everybody see the difference? This is when they move left and right. What does this do? That goes up and down. So we're not as familiar with our logarithmic function. So let me, in black, let me do this, and that's the 0.10, right? Now what am I going to do? I'm going to take that picture and I am going to move it down 2. It goes down 2. This one's going to go down 2. When the number is tacked on the end of the problem, it does what you think it says. So -2 means down 2. So I'm going to take that picture and move it down 2. Now, is that going to change this asymptote right here? No. So the curve is still going to get closer to that, right? The only difference is, what's this point that was 1, 0? Now it's going to be what? 1, -2. So I'm going to have my shape, but it's going to look like this. The same exact shape, just dropped down 2. Remember, the next one is going to be a version of your exponential. You remember, or not exponential, reciprocal. You remember that your reciprocal looks like this? Remember that? If not, look at your sheet there. We did it the other day. Yesterday, maybe. Someday we did it. Okay? Now, what happens when you put a negative in front of it? So this is that. What does putting a negative in front of the function do to it? Flips it upside down. We call that a reflection across the x-axis, but it's just flipping it upside down. So if you take that picture and turn it upside down, won't you get this? So negatives out in front turn you upside down. We call those reflections. Negatives are reflections. Okay, how about this one? I like to sketch my base function, so it normally would look like this, right? That's what the square root looks like. What have I done here with a +1? Pay attention to where that +1 is. What have I done? Moved it up 1. So instead of being at the point 0, 0, it's now going to be at the point 0, 1. It's going to have exactly the same shape. It's going to shoot up from 0, 1. What's your BFF here? The cubing function? So remember what that one is? That's the one that likes squiggles. And it normally would squiggle through the origin. Where's this one going to squiggle through? Huh? Yeah, it's going to go through right here at 2, 0. So you're going to have your nice little cubing curve, but it's going to squiggle through the point 2, 0 because you have shifted it over 2 units. How do we know that's a sideways shift and not a vertical shift? It's inside. When they're inside, they're sideways. When they're outside, they are up and down. This would be a sideways shift. sine x plus 2. Now, this is where it becomes really, really important for you to remember that the original sign, it's oscillating, but it's oscillating back and forth between what? What is its high point and its low point? 1 and -1. So the basic curve has an amplitude, that's the word we use for that, of 1. It goes up 1 and down 1, okay? We are taking that picture and moving it up 2, okay? So if the original high point was 1, then what's the new high point going to be? 3? Everything's going up 2. And if the low point was -1, the new low point's going to be 1. So this curve is oscillating between 1 and 3. So normally it's oscillating across the axis, but I picked everything up 2, so my new axis is like here at 2, and now it's oscillating across that. Is this going to be a left-right shift, or is this going to be an up-down shift? Up-down. If it were going to be a left-right, it would look like this. That 1 would be hooked to the x. Hook it to the x, you're going sideways. Tack it on the end, you're going up and down. So my basic curve, this is our exponential. The basic curve has an asymptote here, goes through 1. So the blue, this is not the answer. The blue is the base curve. That's what I have memorized. That's my exponential. Now, what do I need to do to that curve? Down 1. So instead of the asymptote being on the x-axis, would you agree it's going to be down here at -1? And instead of that point right there being at 0, 1, it's now going to be at 0, 0. And then I have exactly the same shape. My curvature's off a little bit, but you get the idea. I dropped it down 1. And then the last one, negative absolute value. What is the negative absolute value going to look like? That is going to be this, isn't it? Upside down? Okay. Let's answer some questions in our book. We have a little bit of time, we can get started. Let's see. 19. 19 says, oh wait, oh 19, here it is. Identify which of the 12 basic functions are odd. Now, what does odd mean? Symmetric about the origin. So this is number 19, and it says there are 4 functions that are odd. So look at your equations. Look at your pictures, your BFFs, on your paper. Do any of them just look like they have symmetry about the origin? Which ones? Give me one. Absolute value does not have symmetry about the origin, because symmetry about the origin, I understand what you're saying, but symmetry about the origin means that whatever is happening here is mirrored here. It's like 180 degrees. You're going halfway around the thing. Josh?
Linear function.
Linear, absolutely. So the identity, I'll write the equation, but you can write the name, doesn't matter. The linear function, absolutely. There's another one that kind of has that same pattern. What about your cubing function, guys? Isn't your cubing function? If you took this and reflected it across the origin 180 degrees, you're going to get that. So the cubing is another one. I can think of another one, but it's a little trickier. Look at your sine. Look at your sine curve. Would you agree that it has symmetry about the origin? Okay, can you think of another one? I'm trying to think. I've got to look at my list. Oh, yeah. Reciprocal. Yep, the reciprocal function. Clearly that one does, because don't you have the same picture here as here? Yeah, it's kind of embarrassing. I forgot that one. Yeah, the reciprocal function. Okay, let's try the next problem. The 6 functions that are increasing on their entire domain. Chase, head up. The 6 functions that are increasing on their entire domain. So look at your pictures. Which ones would you say are increasing on the whole thing? There's supposed to be 6 of them. Linear? All right, so y equals x, the linear function. Absolute value, now let's think about what absolute value looks like. Does absolute value increase on the first half? No. It increases on the second half for sure, but not the entire thing. Cubing, absolutely. Look at your picture, kids. Trace over it with your finger. Aren't you going up the whole way? Yep, you are. What's another one?
Square root.
Square root, perfect. I got one right here. Isn't the exponential increasing on the whole domain? What's the one that kind of looks like the square root function? The logarithm? And there's one more, but this one's a little bit tricky. This one is a little... Oh, wait. No, it's not tricky at all. It's not, you're increasing on its entire domain. What was the last one we looked at? Logistic. The logistic. Remember, that's the one that's sandwiched between 2 asymptotes. So even though it doesn't rise infinitely, it is still going up all the time. That's the logistic function. All right, we do one more. Let's see what's next. The 3 functions that are decreasing on the interval from negative infinity to 0. Okay, so this one's a little bit more specific. There are 3 functions that as x goes from negative infinity to 0, That's x. So in other words, over here on this side of the picture, you're decreasing, right? Yes, decreasing. So can you think of 3 shapes that are decreasing on that side? Josh? Absolute value, absolutely. Squaring. Is the squaring decreasing over on that side? Sure is. There's one more. Can you find it? It's decreasing on the left side of its picture. What? Reciprocal. Absolutely, Grace. Reciprocal. Think about what the reciprocal looks like. Isn't it decreasing over here? Going down, 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 down? Yes, it is. All right. Good work. Good work. I don't know if we're going to get through all of those before we start doing some other stuff, but that's great. So we need to start memorizing, right, guys?